Thanks for coming. So I'm going to be talking today about a young, pretty fun language that we've been cooking up in the Database Systems Lab at UC Berkeley called Bloom. And I couldn't have done this work, we couldn't have done this work without contributions from everybody in the so-called Bloom team, Neil Conway, our advisor Joe Hellerstein, and Bill Marzak, and without generous gifts from benefactors, including Microsoft. So thank you very much. And keep it coming. I can make short work of this slide with this crowd, I think. I don't need to convince you that distributed systems are hard to program because of these, because of asynchrony, because of concurrency, because of partial failure. And if these systems are hard to program at all, then sort of reasoning about whether their executions are correct is hard squared. And this is an urgent problem now because all systems are distributed. You know, just a few years ago, I started talks like this by saying, with a blanket statement, in the future, all systems will be distributed systems. And I don't even think I need to speculate about the future. We're sort of already there. There's evidence of this both at the sort of microscopic scale of chip scale multi-core and the macroscopic scale in which we're treating data centers and clouds as individual computing units. So we're reaching a crisis. And that's the space where the Bloom language enters. So in this talk, I'm going to introduce this conceit of ours that we call, maybe somewhat provocatively, disorderly programming. The idea is that instead of having users submit totally ordered programs and then trying to relax those orders, we should instead encourage users to, if anything, under-specify order, and then provide tools to refine the program so that you sort of get the order just right. I'm going to do a little tutorial for Bloom, which is our first crack at a language embodying this disorderly programming conceit. I'm going to walk you through some of the static analyses and visualizations that we do of these programs. The idea behind these analyses is to push back at the programmer and encourage an incremental process by which order is restored to programs that are initially specified without any ordering. And then, time permitting, as Eric said yesterday, the only thing that users do online is shop, and so the only thing that we distributed systems programmers need to implement is shopping carts. So let's implement one in Bloom and use our tools to reason about its possible executions. What do we do today? Well, the state of the art today is that we have this model of computation, which is actually a very beautiful model, the von Neumann model or stored program model. It's beautiful because it's simple, it corresponds to intuition, and it provided a meeting ground between architects and programming language designers, right? They didn't need to have crosstalk. They could both think about this model in which we sort of partition our computer into a CPU and memory, and then we further partition our memory into a data segment and a code segment. And the way that computation works is we have a program counter, and it moves through the code segment, which says something like lather, then rinse, and then repeat. And then we do operations on our data. We read memory, we write memory, and we typically use looping constructs to access our data. And so as I sort of have hinted, in the von Neumann model, order is everywhere you look, right? We have a completely ordered array of memory. We have a shopping list of instructions that, at least as stated, need to be done in the order in which they were given. Now, that's great, but it doesn't map very well to a parallel and concurrent world. To make sequential programming languages run parallelly, we don't need to change our language. We can just sort of retrofit our language like you might retrofit a bridge. And there's a couple ways that we do this, but I'll talk about one of them. Threaded programming. So in threaded programming, you don't sacrifice this sequential recipe of computation, but in fact what you do is you make lots of copies of it and let them all run in parallel. But then it increases the burden on the programmer, right? Because now the programmer needs to think about which parallel interleavings are acceptable and which ones aren't. And the way the programmer gives the runtime guidance about which interleavings are appropriate is through locking in critical sections, right? So the game becomes, if you make your locking too coarse-grained, it probably works, but your program isn't performant. If you make your locking too fine-grained, you probably have bugs. That's a big burden. Now, when we move from a parallel and concurrent to a distributed world, the problem gets worse, because in a distributed system, order is a scarce and dear commodity, right? In full generality, the cost of making sure that everything happens in a global order is tantamount to a consensus computation among agents at every step of the computation, right? And that's frustrating because, as I've sort of already hinted, a lot of the order that's given to us by the program is not necessary order. It's order that could be relaxed, and we wish we had the appropriate guidance from the programmer to relax it. Now, the worst thing is that among all that unnecessary overspecified order is critical order, right, for correctness. If I'm implementing a lock manager, my lock manager isn't correct unless I can say in my language something like, you do not grant a lock to someone until the guy who held the lock before him has released it, right? So there's certain things you can't say without order. And the problem is that in a sequential language, the important order is maybe a needle in a haystack. So we're going to try to flip the state of the art around and introduce this idea of disorderly programming. At a really high level, disorderly programming is something you've seen before in languages like SQL and MapReduce. We're going to think about computation at a really high level as just transformations from collections to collections. Okay? So we're going to basically say all state is data, all data is uniformly represented, and all computation, or a distributed service describes a continuous query over that data. So in a disorderly programming language, all of our state is going to be unordered. It's going to be like database tables. And we know that database tables can be partitioned and replicated without regard for order. Our logic, likewise, is going to be unordered. Programmers are going to give us bundles of rules that can sort of be fired in whatever order. And for free, it's not really free, we assume that all these statements are independent, and so we get concurrency for free. Now, as I said, sometimes we're going to need to restrict the order in which some of the rules can fire. We're going to want to restrict the order in which certain data elements can be stored. When the programmer wants to restrict order, they have to do so explicitly. There's a sort of programming language design maxim that the right language for a particular domain should sort of obscure the details that don't matter and bring into focus the details that do. And we feel very strongly that ordering is the hard detail about distributed systems programming. When a programmer says they want order, they should be thinking really hard about what order they want. So it's sort of a special case behavior that, this is where the cognitive load of the programmer should be raised. So we're presenting Bloom. Our first cut at Bloom we call BUD, which stands for Bloom under development. We've implemented it as a Ruby internal DSL. We're not tied to Ruby. Turns out Ruby's a really easy language also to screw around with syntax for DSLs. As we've gone further and built bigger and bigger artifacts, we kind of wish we had a type system. But it was a good place to start. In Ruby, it's really natural to express transformation-oriented computation using, sort of map and reduce like primitives. So I say, this collection is defined as some mapping or grouping over this other collection and so forth. Now, it has a declarative semantics. I'm not going to get into this in this talk. This is a long conversation. But I'll just say that what I mean in this case by declarative is something pretty specific. I mean that you can reason about the meaning of a Bloom program without reasoning about its evaluator and its executions. And if that's surprising to you, that I have a language for programming distributed systems where you don't need to reason about executions, that's good. It should be surprising. And we should talk about it offline. Now, having briefly advocated declarativity, I'll also point out that for most programmers, myself included, it helps to have an operational model in mind when you write your program. So that, it helps to have a mini evaluator in your mind to think about what happens when you run your program. And although we have a declarative semantics, it maps to an operational semantics that goes something like this. Over time, a Bloom node, a single agent that's executing this global program, accumulates updates from the external world. These updates may be in the form of messages that other nodes have sent it. They may be in the form of timers firing, local clocks firing, or deferred updates from itself from a previous time step. At some point, we sort of freeze time, take this batch of updates that have accumulated over time, take the union of them in our local database, our local state, and we fire all of our rules until no more rules can fire. We do like a fixed point computation if you're familiar with logic programming. Now, this is not just a simple event loop because some of our relations may have been recursively defined. So we may need to go around this now loop a few times to reach fixed point. When we do, when we finish our atomic local computation, we've generated maybe some list of events that need to go out. Messages we need to send to other nodes, deferred deferred deductions that we need to give to ourselves at some future time step. And in fact, as I'll show, this is the only construct that we have in the Bloom language for sequencing. In general, you talk about all these things happening. Given what you know, what else do you know? Sometimes you say, given what you know, what do you know later? And so you may have enqueued updates for yourself. So you proceed through these sort of big logical time steps and do local deduction. And at the boundaries of that, you interact with the external world and with other agents. So sort of a observe, think, act. Now here is a Bloom rule that defines multicast as the join of a collection of messages and a collection of group members. All Bloom rules have this form, in which there's a left-hand side in which we define a collection. Now, there's a bunch of different collection types. I'm not going to go into too much detail here, but at a high level, a collection might be a persistent collection like a table in a database, where if we put things in it, they stay there till we explicitly take them out. Or it might be a transient relation like a view. We put things there and they stick around for the fixed point computation, and then they disappear. It's sort of an intermediate temporary variable. Or they may be a special case transient, a channel that represents the movement of a record from one network endpoint to another. Now, if you define a channel, we insist that one of the attributes of that record be an address so that we know how to ship that tuple to another location on the network. Now, over on the right-hand side, we see something also familiar from databases. We have a from list. In this case, we're saying it is the join, or really the cross product, because we haven't restricted the join between message and member. So you have 3 members in your group, you have 1 message, so the cross product of those 2 things is going to be 3 rows that combines the tuples. And on the right-hand side, we have some arbitrary Ruby expression. So far, this really looks like a little bit like SQL, where the user-defined functions have been hoisted up into the query itself. So you just write arbitrary Ruby on the right-hand side. All we're doing here is really using a tuple constructor and saying this right-hand side returns tuples that take the address from the member table and the ID and payload from the message table, and those go into multicast. Now the interesting detail is the accumulator. So we're saying, as I said before, we need to specify temporal details of when the conclusions deduced by the right-hand side appear in the collection on the left-hand side. In an ideal world, all our programming could be disorderly. We never have to talk about order ever. And we could always use this now operator. Given what I know, what else do I know? But in practice, sometimes we need to sequence things. So we have a next operator and a not next operator that corresponds to deletion, where we say, based on everything I know now, what must I know in a deferred fashion at the next visible state of the database? And this is our primitive for expressing sequencing. We use it sparingly. Maybe most interesting to the domain of distributed systems is this later operator. The idea of the later operator is modeling network non-determinism. The deductions or the conclusions reached by evaluating the right-hand side appear on the left-hand side at a different place at some unspecified future time. And, Bud's a little language, but it has to be usable. So we did something that most logic programming languages don't do. We provided a means of abstraction and encapsulation. It's nothing fancy. We borrowed from Ruby's mixin system. So you can define units in which you've sort of said, these are the inputs to this data flow, these are the outputs to this data flow, so that you can reason at the level of the modules, stitch together modules. You can separate interfaces from concrete implementations so that a particular interface can have multiple implementations and so forth. This is nothing interesting to this crowd. Something nice that falls out from a language in which you've reified all your state as data is that you can do lots of fun stuff with metaprogramming, and we've explored this in future work. So if my AST is also just tables, and I have a query language, I can query my program, that's reflection, and I can update my program. So I can express program rewrites within my language. For the NoSQL crowd, we have schemas, but you don't have to use them. If you want to define a collection, its default schema is key value. And you can sort of add schemas in a sort of pay-as-you-go fashion when it becomes too confusing for you to be managing all these collections whose schemas are key values, but the keys and values mean different things. You can name them, okay, if you want to, but you don't have to. And then the most important thing is it ships with some visualization tools that allow you to reason about, first of all, what data flow, what high-level data flow does my program text induce? And then, should I be concerned about the consistency of that data flow? And I'll talk about this in detail in the rest of the talk. So here is a delivery protocol in Bloom. This is an abstract interface. And so it really just looks like sort of a schema declaration, okay? It is a delivery protocol, and what is a delivery protocol? Well, a delivery protocol is a thing that you can put data into, and the data gets shipped somewhere, and then maybe, hopefully, you have some way of knowing whether the shipping was successful. So we have an input interface, which is a unidirectional transient called pipe-in. It has 4 columns. There's a destination address, where the tuple is, where the record is bound for. There's a source address, the sender address, return address. There's a unique identifier for the tuple, just as is the style. And the tuple has a payload. And this implication operator is actually a functional dependency. So we're saying the destination, the source, and the identity uniquely identify the payload. Or from a database, in database language, dest source ident is the primary key. There are no combinations of dest source ident that have different payloads. We have 2 output interfaces corresponding to the 2 network endpoints. They have the same schema as pipe-in. Pipe-sent is the sender's interface. When I put a tuple in pipe-in, I know that transmission was successful when I see that tuple appear back on pipe-out. On the receiver, when I see a tuple on pipe-out, that was a tuple that's come to me from the external world. And given this specification, we can only draw this picture. So data flows into the system, it goes into pipe-out, pipe-in. Something undefined happens. By the way, you need to fill in this hole because this isn't a fully specified program. And then it goes to 2 places, pipe sent and pipe out. And here is a concrete implementation of that protocol. We include the interface. We define a piece of private state, a channel collection called pipe-chan. And we say, when a tuple comes into pipe-in, send it. Now look at the last rule, when a tuple appears on pipe-chan, report it at the receiver endpoint. And because this is a best effort delivery, we're just going to declare victory. As soon as we try to send the tuple, we say that we succeeded in sending it. Obviously, a reliable delivery would have retry and acknowledgement and so forth. We say, if you have a tuple in pipe-in, declare victory. And that's best effort delivery. And it draws a picture something like this. Tuples come into pipe-in. They have 2 possible paths. One, which takes them across a dotted line, an asynchronous edge, and one synchronous edge. And our data flow has warned us about the asynchrony and tainted the downstream flow. I guess it's usually yellow, but you can't see yellow, so it's orange. Slow down or go really fast. And I'm going to get into why we care about that. I'm going to go fast through this, but here's another example of a Bloom program. This is a protocol for a key value store. Okay, well, what's the external interface of a key value store? Well, you can do puts, dels, and gets, right? And puts, you associate keys with values. And when you do a get, presumably you get a response, right? So you do a get for a particular key, you get that key and its value back. That's the externally visible interface of a key value store. And the picture that the interpreter draws is the picture that you would expect. There's 3 ways in, there's 1 way out. And please specify an implementation of the key value store, which we do here. So for our internal state for the key value store, we just need 1 persistent table representing the mapping between keys and values. And then the rules are pretty simple. We say, if you get a put in the next visible state of the database, not now, next, the state will reflect that mapping of key to value. Oh, but there's one other thing. There might have already been a value with that key, right? So if there is a value with that key, you're going to have to clean it up. So we say join state with the put on key. And if there is a tuple, so 3rd line down, or 2nd line of mutate, take state, join it with put, make them agree on key. If that generates any tuples, those tuples should disappear from KV state at the next visible state of the database, concurrently and atomically with the insertion of that new tuple. Okay? And get, same thing, right? If you get a get, join it with your state on key. If they agree, send it back to the client. And delete, same thing. If you get a delete, join it on state on key, and make it go away. And here's the picture. 3 ways in. 2 of them go in. 2 of them affect the state of KV state, and the 3rd one reads the state of KV state. And our interpreter has warned us there is non-monotonicity here in the data flow. You might care about that. It was easy for our interpreter to spot the non-monotonicity. It is a syntactic property. If you do a put, you might do a deletion. If you do a deletion, you might do a deletion. Okay. So I'm going to do a little tutorial. I'm going to try to go fast through it because I think this is pretty obvious stuff to you guys on why we care about asynchrony and non-monotonicity in distributed systems. So the issue with asynchrony is that there's uncertainty, right, about whether you've received all your messages, when you're going to receive all your messages, and the order and timing in which you're going to receive your messages. So this is sort of what's hard about distributed systems, right? But I want you to take away from this talk that it isn't necessarily hard. It depends what logic is downstream. It depends what you do with async-derived inputs, okay? So as tuples appear on the left-hand side, they appear in some weird order on the right-hand side, and that may or may not mess things up for you. Now, I talked a little bit about monotonic logic yesterday. Monotonic logic, if you pick the right language, is easy to spot, cheap to spot, at least conservatively. The more you know, the more you know. As my inputs grow, so also does my output. This means that, if I have employees on the left-hand side, I have employees on the fourth floor on the right-hand side. As I learn about more employees, I learn about more employees on the fourth floor, right? If I want to define employees' email addresses as the first letter of their first name and then their last name at Microsoft.com, that's some function of my input, and so as I learn about more employees, I learn about more email addresses. Likewise with join or composition, right? If I want to know my employees who are also officers of the company because I have to do a report for the SEC, as I learn about more employees and I learn about more officers, I also learn about more employees who are officers, even though there might be orphans on both sides, right? And so here are some corollaries of that, of what I've just said, that maybe are obvious, but I'll say them anyway. Monotonic logic doesn't care what order its inputs arrive. Here's an execution where they arrive in different orders and produces the same result. Monotonic logic is sort of eventually consistent, according to some definition of eventual and consistent. Maybe more practically for a systems programmer, monotonic logic is pipelinable, which means you can act on conclusions as soon as they arrive, even if it means dispatching computation that you can't retract. Okay, so this is just a picture that shows these conclusions going somewhere and doing something outside my scope. That's totally safe, right? Now, non-monotonic logic is all logic that doesn't have those nice properties, that my outputs may shrink as my inputs grow, right? So the canonical example is set minus. As I add to x, if I define z as x minus y, there's a great deal of uncertainty about what I can assert in z. So here I'm sort of eagerly asserting things in z, and as something appears in y, I have to say, psych, sorry, I hope I didn't spend too many resources speculating on that, and I hope I didn't tell anybody from whom I can't take it back. So the obvious corollaries, right? Here's another execution of the same program with the same input in which I don't have to do those retractions because the tuples happen to have appeared in some angelic order, right? And in practice, what we do, certainly in logic programming systems, what we've done historically is you play it safe, right? You block, you wait till you know. So I have A in this set. Can I say that A is in this set? Well, the question is, will A ever be in this set? And so in practice, what I'm going to do is, I'm not going to say if A is in my output set until I can seal the input that I'm taking the complement of, right? Once I say this is never going to change anymore and A is not in it, I can say that A is in this. Okay? So COM analysis just puts together these two really simple observations about asynchrony and non-monotonicity and what their sequential composition looks like, right? So asynchrony implies we sacrifice order. And we draw you a data flow in which we represent asynchrony as dotted lines, and we taint downstream results as yellow, slow down or go real fast. Non-monotonicity implies a computation that may be sensitive to the order in which its inputs are seen. Okay, you might care about that too. So we're gonna draw a special arrow for non-monotonicity too, and we're also gonna taint downstream data as non-monotonic. Now here's the issue, right? When asynchronous data flows into a non-monotonic computation, when you do something that loses order, and then it turns out you cared about the order, That's what makes distributed systems hard, okay? We're gonna taint that data as potentially inconsistent. Now, what do I mean by inconsistent? Well, I mean something really simple right now by inconsistent. I mean non-deterministic, like you run your program, you observe a bug, you run it again, you don't see the bug. You don't know when you're gonna see the bug again because you get different orders on each execution and then you commit to an order. In terms of replicated systems, this non-determinism manifests itself in a single execution, right? Because I'm replicating my data to a bunch of different systems. Depending on my choice of replication protocol, the different systems may see different delivery orders. So in fact, I may have a distributed key value store where my replicas don't agree on the state of the database, even though they've all seen all the updates, which would be unfortunate. So we call this last chance to put the order back a point of order. And we flag these specially in our visualization. So lots of computation and communication can happen as we flow through this data flow. You might be able to get away with doing some really cheap replication out here. But before you do anything with the downstream data, you might need to be extra careful. We call that a point of order, or a POO, if you like. But what do you do about a point of order? Well, I already hinted at one of the things you do, the conservative thing. You sort of ask, right? You coordinate. You run a round of two-phase commit, or Paxos, or you run all your updates through all your messages through a group communication system that makes sure that they get delivered in an order that your application needs because you know something about your non-monotonic operator. And this corresponds to the ACID tradition, right, in databases. You build a really big system infrastructure that guards the orders in which things can happen, and the application programmer can rely on that and write fairly simple programs whose cost, as the system becomes more distributed, might be too great to bear, right? So if we think we can't afford, we don't want to be acid heads, maybe we'll be base heads and sort of beg for forgiveness, right? So we can let the data pass that non-monotonic operator, and maybe we'll taint it, and maybe we'll say these are tentative conclusions. Maybe we have resources to spare. We want to speculate past that boundary. We just need some mechanism for cleaning it up. Now, that mechanism is obviously going to be a lot more application-specific than our coordination was. So it's going to be a little harder, but we may have to choose this. Regardless of which of those two things we choose, having programming tools that tell us exactly where our last chance to repair order is allows us to play games with data flow rewriting, right? Like, I might not be able to remove the non-monotonicity from my program, but I might be able to rewrite my program in such a way that I've pushed that circle up or down the data flow to a place where empirically it's going to cost me less to enforce it. It's going to cost me fewer rounds of Paxos, maybe, or it's going to cost me simpler and more general compensation logic for merging inconsistent updates. So in the time remaining, which is not much, I'm going to demo a shopping cart application in Bloom and use these tools to reason about its executions. Why replicated shopping carts? Well, why do we replicate data? We replicate data because some of our servers might go down. We replicate data because we want to serve data from a server that's close. Okay? And the trick, as I said, is that the replicas may see the messages in different order, so how do we make sure they agree on the state at the end of the day? When's the end of the day? Oh, it's when a checkout comes, right? We know when the end of the day is in this application, and we can use that. And we all read the Dynamo paper, right? We know that there's a sort of best practices for how to build these things. We can't use all immutable data structures because carts aren't immutable. Not all updates commute. But we can reason about when updates commute, try to keep our coordination costs low. But we don't have concrete tools to help us in this process. We have to use, distributed system programmer genius to do this. So can we help with that? Here's a shopping cart protocol. I won't spend too much time on it, but you have a stream of actions from the client. For a particular session or cart, you have some item, beer, diapers, and some action, add, delete. And at some time, that session checks out. And when that session checks out, the server, whatever replica the client happened to be talking to, sends a response to the client that contains, yeah, for that session, you have beer, 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 diapers. And here's the picture, right? It's obvious. There's two inputs, and there's an output. So we're going to roll the carts two ways. The first way is the obvious way, the stack-based way. Well, we already have a key value store, so wouldn't a natural way to capture a cart be to say the key is the cart, the session. The value is a running array of contents of that cart. And then when we get a checkout, you just sort of ship, thank you, you just sort of ship that value array back to the client. That's pretty simple. And then the second time, we're going to apply this sort of dynamo wisdom to say, commutative updates are good. How can we make carts commutative? And we're going to do something like, oh, no, as you get updates, you're going to sort of just lazily append them to an append-only log. And then when you get a checkout, you're going to summarize that log. Now, checkout's going to turn out to be a non-monotonic operation, too. But we've postponed that non-monotonic operation until we know that the session is done. So here's the Bloom code for the destructive cart. It's quite short. It refers to the key value store, but you've already seen the key value store too. So you can imagine unpacking that into the complete destructive cart. I don't really have time to talk too much about it, but it's what you would think it would be. When you get an action, probe the key value store and see if you already have a record for this session. If you do, append to that array or delete from it, depending on what the operation was. If you don't, create a new record in the key value store. And so, we're doing a bunch of work on update. We're eager update, right? And then a sort of very simple checkout, right? When you get a checkout, probe the key value store. And if you find a record in the key value store, just ship it back to the client. Okay. So first thing I'm going to say is, this is the picture. We see that the data very quickly gets tainted with asynchrony because it immediately crosses an async boundary going to the client. And then we see this sort of cyclic data flow. Why do we have a cycle? Well, because KV state is defined in terms of itself. And the data downstream, immediately after we get an action message, we do something non-monotonic. We remember what that was. And actually, so first thing we do is we're going to collapse that cycle because it doesn't have any semantically meaningful information. If you have a cycle that's non-monotonic, then there are paths around that cycle. If you have a cycle, one of whose edges is non-monotonic, then there is a path through that cycle that touches that edge. So we're going to conservatively assume that it's sort of just a single node. We're going to collapse the strongly connected component and say that thing is non-monotonic. There's no way to get from KV put to client response without doing something non-monotonic. Okay? And our tools tell us, well, gee, there's asynchrony, right? And then there's non-monotonicity. And so our results are divergent. What do we do? Well, let's say we choose the conservative route. We're acid heads. We're going to put 2PC in there. We're going to put Paxos in there. Or we're going to put synchronous replication in there. We're going to interpose in our data flow. And we can synthesize it for you, actually. It won't be the most performant coordination, but we can synthesize something for you in the flavor of 2PC. And what's that going to cost us? Well, I know something about a shopping cart. I know that there's some number of actions, and then there's one checkout. And if I look at the flow on this edge, it's the same cardinality as the actions. So it's going to cost me n rounds of Paxos. Yeah, n is not going to be a very high number. Here's the disorderly cart. In the disorderly cart, I don't do very much at all when I get an action. I append it to the end of the log. When I get a checkout, as I said, I do quite a bit. I sort of, at a high level, for every session, for every item, I count up the additions and deletions for that item. I take their difference. I construct an array out of that set, and I ship it back to the client. Here's the picture. It's a simpler picture. There's no cycles. But there is non-monotonicity corresponding to aggregation in the data flow. So at sort of the top level, the analysis tells me the same story, right? Asynchrony followed by non-monotonicity leads to divergent output. Okay? What's it going to cost me to fix? It's going to cost me one round of coordination because I don't cross that locus in the data flow until I get a checkout message. Checkout messages gate the flow of data across the non-monotonic boundary. And finally, when I extend that simple disorderly cart with full-fledged replication, so here's a picture of the program that adds order of half dozen Bloom rules to make sure that I'm you've sort of already seen them, that I'm multicasting to all my replicas. So, there's a distinguished replica who gets the update, he multicasts it to his peers. The data flow gets a little bit more complicated. In particular, we added this replication code in this section, but this is cheap replication. I'm replicating to the servers before I've had to do any coordination. And the shape of the data flow downstream is the same shape of the data flow we saw in the previous picture. We have one round of coordination that we need to do at checkout. So if I had time, and I don't, I would love to tell you about my experience teaching. Yeah, I would love to tell you about my experience teaching an amazing group of undergrads a distributed systems course last semester where we used Bloom as the instructional language and forced them to be a captive audience. It was really fun. Some things worked better than others, but in the end, we got a lot of great bug reports, and we got a really nice set of concrete code artifacts. Stuff like quorum replication for key value stores. They implemented Paxos. They implemented, vector clocks, leader election, two-phase commit, lock managers, deadlock detectors, all sorts of fun stuff from sort of distributed systems and databases domain, since that's where we're coming from. And like I said, they were a captive audience, so I don't think we can quite count that as adoption yet, but it's a young language. And so, as is the style, I'm going to end this talk by asking a bunch of questions and answering them. So why did I choose a provocative word like disorderly to describe a language that I want, principled people to use? And it's just to emphasize the fact that order is something that we should be really stingy about using in distributed systems. We should start by specifying programs logically as a set of implications, and then refine those programs with the help of tooling. Okay? It's at some level the opposite of what we've been trained to do. Okay? Well, I just said that order was distracting. Order's not the thing. Well, if order's not the thing, what is order for? Well, I hope I've convinced you, or at least put a doubt in your mind that it might be the case that order is necessary when we do order-sensitive computation. And if you choose the right language, that's something that's easy to spot. Okay? I talked about this idea of coordination. I sketched some examples of coordination that we see in the wild. What's the point of coordination? I hope I've put a glimmer of doubt in your mind that maybe coordination really fundamentally locks, right? And consensus computations are fundamentally to control order flowing into non-monotonic processing so that we get consistent results. And by consistent results, I mean deterministic executions to make trace and replay easier. I mean consistent data in replicated systems. So I hope you maybe believe that Bloom implies calm. Bloom is a disorderly programming language that ships with tools that help you get the order just right. And if you're interested, we've written a bunch of papers about this, some more theoretical, mostly more theoretical than practical. Although, if you're interested in practical stuff that demos this language, I encourage you to look at our CIDR paper. And I guess I have time for a couple questions.
Is that boom or bloom on the slide? Last slide.
My group is called Boom, Berkeley Orders of Magnitude.
I'm glad I asked because I thought it's a typo.
Yeah. Berkeley Orders of Magnitude. Orders of magnitude larger systems with orders of magnitude smaller code. That's the pitch.
Hey, so I'm real interested in the tool you showed with the graph, with the stratification graph. So at LogicBlocks, we use a similar programming language, and we're finding that you may run into them. And the graphs tend to have about 5,000 nodes in them, about 5,000 rules. And indeed, we're not so worried about monotonicity for performance reasons, although that's certainly important. But it also kills stratification, because if you loop through something through a negation or an aggregation, the program gets rejected, and the programmers are spending a ton of time tracing through with no tools. So I was wondering if have you experienced what kind of size of programs have you tried the tools on, and what do you do when it doesn't fit on a screen any longer?
Right. So one approach is to draw the graph. So not 5,000 nodes, but LogicBlocks is a really cool company, by the way. That's awesome. Order of 100 nodes, maybe biggest ones that we've done because we've mostly built toys. One approach is, as I mentioned, we have a module system, and you can sort of reason, because the modules have well-defined inputs and outputs, you can treat the modules as nodes in a graph, right? First of all, you can attribute to does the module have negation in it? Then you kind of need to mark the whole module as a non-monotonic operation, right? Does it have asynchrony in it? So you propagate those labels upwards. But then you can reason at whatever level of abstraction you think is appropriate and draw the graph at that level, and then sort of zoom in to ask questions about what's going on in this particular module. That's how we That's how we solve that. As far as the stratification issue, we do allow cycles through negation because obviously in distributed systems, you see patterns like that all the time. I send you a message, you do something non-monotonic, you send me a message back, now we've got a loop. We require that all such cycles be broken by a temporal edge, you see? So we get local stratification on logical time.
Not being very familiar with the concepts that you presented, I was curious about understanding, of course, the shopping cart example is a toy, but the time scale that it occurs on, in a typical implementation, you would probably want to monitor the state of the system while you're building your shopping cart. And in the
so who's you? Is you the client? Like,
yeah, like the actual person using the shopping cart.
So the sort of the dismissive answer that I have ready for that question is that's a perfect case where you might allow tainted results to go back to the client, like current status of my shopping cart, and you actually don't care if it's not told. Like if they connect to a stale replica and they see an earlier version of the shopping cart, it's not the end of the world. Mm-hmm. So that's a perfect example where you might tee the system into one place where you ask for forgiveness, right? You maybe display on the client's browser some stale results, but before you go to Visa, you ask for permission.
Right, and you confirm.
Yeah.
But say it's a requirement that you do always present a valid shopping cart or some analogous system. How those points of order that you were showing, I'm assuming that each one is treated independently. Like you can resolve the system state for one point of order and leave the other points of order perhaps unsettled.
Yes, yes, of course.
And how can you introduce, say, no, I really need, if the second implementation of the shopping cart you provided, you could have a situation in which you were getting stale data via a query. How can you say, no, really, I want to introduce a point of order here?
I'm not sure I understand the question, because if I wrote that query that summarized the cart, that query would manifest non-monotonicity. I'd spot it. I'd put a point of order there. So some level, I have a T in my data flow. I have a point of order here. I have a point of here. They're independent. But then if I do something non-monotonic downstream, I have a point of order down here too, right? Where they converge. Maybe I'm not understanding your question.
I guess I was trying to.
I can't express a summarization without non-monotonicity. So it would be manifest in the graph. Okay. And then the question would be, what do you do about it? And as you say, yeah, it's very likely that you might say, I don't need to be as careful when I'm displaying incremental results to the client as I do when I build them.
So choosing to take the less careful approach wouldn't remove the non-monotonicity. It would just be a way of dealing with it.
That's right. I don't get into this in this talk, but when you, say, synthesize coordination or ask the programmer to interpose coordination by hand, you don't just sort of take away the point of order. You put in a new annotation. Because really, coordination doesn't just clean up the orders that were upstream of it that you were concerned about. It cleans up anything going into it, right? So I wouldn't want to forget that I had coordinated some label in the data flow, because it can clean up other things that are flowing into it, not just the thing I thought I was fixing.
Okay, thanks.
One last question.
Really quick question. Firstly, this is very cool, so thanks. Do you have the sort of underlying computational model for Bloom written up somewhere? Like, for example, it sort of reminds me of like joint calculus in some way, but then you have other structure. You seem to have channels and sort of
That's right.
messages
So,
through channels.
We basically, our model is a data log variant extended with some minimal temporal logic constructs.
I see.
Okay? And so the model is, you've reified every tuple sort of secretly has a location and a time variable. You enforce that all rules join on those things to enforce locality of visibility and locality in time. And then the possibility of executions producing different outputs due to temporal non-determinism is expressed by the logic program having a multiplicity of stable models. And we can talk about this offline. I encourage you to read the paper also.
All right, thank you.
All right, well, thank you very much.
Thanks.